Okay, well, let's try breaking the normal assumption even more. What if I have a uniform distribution on the left, so equally likely to be anywhere between these 2 points, and an exponential distribution on the right, where it's very likely you get a point around -1 and then less and less likely as we get up toward 4. Both these distributions have mean 0 and variance 1, and I'm going to select 50 points from each of them, but the normality assumption certainly isn't true, and yet everything still works totally fine. 5% of the time, I get a p-value less than 0.05, and therefore reject the null when it's actually true. Because the null is true in all these cases, right? The means are 0 in both population distributions. So the null hypothesis of equal means is actually true. This normality assumption for the t-test isn't so important. Okay, so let me continue to use these 2 distributions that are definitely not normal. They're different from each other. Let me draw 10 values here and 30 values here. What happens then? Now we're starting to break the normality assumption. Finally, we're starting to find a situation where we might have a problem. If the distributions are different from each other and they're both vastly non-normal and the sample sizes are small and also not equal to each other, maybe we'll have a rejection rate a little bit higher than intended. So t-tests are fairly robust at departures from normality, especially when you have large samples. When the sample sizes are not equal, that's when t-tests are going to be a little bit more sensitive to these distributions that are not normal. For small samples, t-tests are going to be somewhat sensitive if the 2 distributions lean different ways, if they're skewed in different ways. How do you check? Take your data set and make histograms. You don't need tests for normality. Tests for normality exist and they're often taught in statistics classes, but honestly the cutoff for rejecting a p-value is arbitrary anyway, so I don't suggest using a test for normality that has some cutoff to decide whether normality exists in order to then use your t-test that's going to use another arbitrary cutoff. It's an extra step that isn't needed and makes an arbitrary decision rather than informing yourself based on what's actually there. I suggest checking the normality assumption based on making a histogram of the sample that you have for each group, and if they look kind of normal, you're probably okay because as you've seen, this normality assumption is not that important. So when this assumption of normality is violated, the t-test is usually still fine. You could use a non-parametric test, or you could transform your data by taking the log or some other transformation. Here's some examples of checking for normality. I said you could make a histogram. You could also make a box plot, or here on the right, this is called a normal quantile plot, where you take all the values in your data set and sort them, and you plot the lowest value against the corresponding value that would be lowest if this were a normal distribution, and then the second lowest value against the value that would be second lowest if this were a normal distribution, etc. And if this is a straight line, you have normality.